An interstellar visitor just skimmed past the sun, and it didn't behave like a quiet traveller. As 3i Atlas swung through Perihelion, spacecraft watching from space saw it brighten fast, its gas halo surged, and its strange tail geometry shifted again. What exactly happened, and what does it tell us about a comet born around another star? Let's break it down. Imagine looking up at the night sky and realizing that one of those faint drifting smudges of light is not from here, not from our sun's family, not from any orbit that loops back for a return visit, but from someplace so far away that even our language starts to feel small. That's the story of 3i Atlas. It isn't a regular comet paying a routine call. It's a message in motion, a traveller from another star passing through our neighbourhood once and then gone for good. When astronomers first flagged it, the details sounded almost familiar. A fuzzy glow, a growing tail, the telltale breath of gases escaping as sunlight warmed its surface. But there was something different hiding in the path it traced across space. Instead of drawing an oval that would eventually close on itself and lead the object back around the sun again, its path opened outward like a sling. That open path told us one thing with absolute clarity. This visitor is unbound. It isn't tethered to the sun at all. It's just cutting through our cosmic backyard on its way somewhere else. To feel the strangeness of that, think about how most comets live. They're snow and dust relics from the sun's own youth, parked in distant reservoirs until a nudge sends them inward. They fall, they flare, they leave, and given enough time, they come back. 3i Atlas breaks that pattern. Instead of belonging to our family, it's like a stranger stepping off a fast-moving train, gliding across the platform and hopping onto another train without ever stopping. By the time you really register what you're seeing, it's already disappearing into the dark. The name hints at its origin story. 3i Atlas means it's the third interstellar object confirmed by astronomers, and it was spotted by the Atlas Sky Survey, an automated sentinel that sweeps the heavens every night searching for anything new, anything moving, anything that might matter. Atlas is built to find threats, but it also finds wonders, and this time it found a wonder that raises more questions than answers. What kind of world formed this object? How long has it been travelling between stars? What stories are locked inside its ices and dust? Calling it a comet is useful, but it's more like a portable time capsule from another solar system's childhood. When starlight, our starlight, struck its surface for the first time, those ancient ices started to wake up. Gas seeped out. Dust lifted away. A thin atmosphere called a coma swelled around it. A tail stretched back, shaped by sunlight and the steady push of the solar wind. Each of those changes is like a fingerprint. The way it brightens, the mix of gases that leak out, the sizes of the dust grains that break free, together they sketch a biography, telling us what 3i Atlas is made of and hinting at the place where it was born. What makes this especially exciting is comparison. We've had so few confirmed interstellar visitors that every one of them rewrites something in the textbooks. The first was a weird, tumbling object, without a clear coma. The second looked more like a classic comet with a generous envelope of gas and dust. 3i Atlas is the next piece in that puzzle. If it shares traits with the others, we learn what's common among comets from different stars. If it diverges, we learn how wild and varied planetary kitchens can be. Either way, we're not just studying a single rock, we're sampling the menu of the galaxy. The motion itself is a kind of poetry. Even without crunching any hard math, you can imagine the speed from the shape of its path. A bound comet slows as it climbs away from the sun and speeds up as it falls inward. But it's always playing a game of cosmic catch and release that ends in reunion. 3i Atlas isn't playing that game, it's on a one-way sprint. The sun bends its route, yes, but can't capture it. Gravity gives it a curve, not a leash. That's why astronomers talk about it as a rare chance, not a recurring show. Miss your observations now and you miss them forever. And so telescopes turned. Robotic observatories watched for the slightest flicker, Spectrographs, those instruments that split light into its hidden colours, looked for chemical breadcrumbs in the glow. Spacecraft designed to stare at the sun kept an eye on the region around it, hoping to catch the visitor in a brief, blazing cameo. Each data point adds a brush stroke. Brightness over time reveals how quickly the surface layers respond to sunlight. The presence of certain gases tells us which ices thaw first. The behaviour of the tail hints at the mixture of fine and coarse dust that's being blown away. There's also a human thread running through all this. The discovery image, the alert note, the sudden scramble to book observing time, these are the quiet dramas scientists live for. A new world appears, and for a few weeks or months the global astronomy community becomes a relay team. Someone catches it at dusk when the sky's still bright. Someone else follows in the darkest hours after midnight. A solar spacecraft picks it up near the glare. A large telescope gathers a spectrum that no backyard instrument could hope to see. The baton moves around the world from hemisphere to hemisphere until the window closes and the data set is as complete as we can make it. And what about size, shape, and surface? Those are always the slippery details. With something this distant and small, we usually infer more than we directly see. A point of light that brightens and fades can stand in for measurements we can't make. A rough sense of how large the active area is, whether crust is cracking to reveal fresh ice, whether jets of gas are turning the body like tiny rocket nozzles. If you've ever watched a garden hose kick when water blasts out, you've got the right picture in your head. Comet jets can twist a nucleus and make it wobble. That wobble can change how the sunlight falls, and that can change the activity again. It's a lively dance, all happening on an object so small that even our best images reduce it to a glowing speck. Because it's interstellar, there's an extra layer of mystery in the chemistry. Comets from our own system are a patchwork of water ice, carbon-bearing ices, and mineral dust. 3i Atlas almost certainly has those, but the exact recipe matters. A little more of this gas, a little less of that one, and suddenly you're looking at a fingerprint that doesn't match our local family quite as neatly. That's the quiet promise here. By reading its light, we might learn how other stars bake their comets, how warm or cold their nurseries were, and whether the building blocks of life, simple organics, are common ingredients in the galaxy's pantry. There's also the simple emotional awe of it. 3i Atlas spent ages in deep space, chilled and silent, drifting between suns. Now, for a handful of weeks, it's lit by our sun, seen by our eyes, and studied by our instruments. Then it will fade again, slip past the outer planets, and return to the grand, dark sea. We will keep the measurements, we will keep the charts, and the plots, and the carefully written papers, but we will also keep the memory. Our little world watched a traveller from somewhere else, and for a moment we were connected. Our light warmed it, its light reached us. So when you hear the name 3i Atlas, think of more than just a label. Think of a messenger with no words, telling a story in gas and dust. Think of a bridge between solar systems. Think of how rare it is to catch a snapshot like this, and how much it teaches us about where we came from and how many different ways there are to make worlds. This is not just another comet. It is a once-only visitor from the wider galaxy, and meeting it, really meeting it, means listening closely while it hisses, brightens, changes, and then moves on, carrying the rest of its tail to places we can only imagine. Mark your calendar in cosmic ink. The key moment happened in late October 2025, when 3i Atlas swept past the Sun at its nearest approach. Astronomers call that moment Perihelion, literally the point when a wandering body grazes closest to our star. For this traveller, that instant fell around October 29th to 30th, and it wasn't a dive straight into the furnace, but a careful skim, staying well outside Mercury's scorched racetrack. Think of it as a flyby through the inner solar system's suburbs, close enough to wake the ices, far enough to avoid a meltdown. Now, how close is close in space? Picture the Earth-Sun distance as one handy yardstick. Astronomers call that one astronomical unit. At Perihelion, 3i Atlas was about 1 1/3 of those yardsticks from the Sun, roughly between Earth's orbit and Mars's. That's the sweet spot where sunlight is strong enough to stir dormant ices, yet not so fierce that the nucleus gets stripped bare at once. In practical terms, that distance meant it was active and interesting, but never a spectacle for unaided eyes on Earth. Here's the catch. When the big day arrived, we couldn't watch the show directly from home. From our vantage point, the comet slid into solar conjunction, lost in the sun's glare, hidden behind our star's blinding spotlight. Ground telescopes and even many space telescopes near Earth had to sit this one out, like trying to follow a firefly fluttering right across a stadium floodlight. The timing was impeccable for the comet, and inconvenient for us. But the solar system is not short on lookout posts. Spacecraft scattered far from Earth had the geometry we lacked. Probes near Mars were particularly well placed because 3i Atlas had just swept past the red planet's neighbourhood a few weeks earlier. Other deep space missions, on their own long journeys, could stare toward the Sun from angles we can't get from Earth, keeping the comet in view as it rounded the bend. In other words, while we were squinting into daylight, our robotic scouts elsewhere had front row seats. Talking about distance also means talking about what we didn't get. No dramatic near miss, no bright bead arcing across twilight. The comet never came especially close to Earth, and that makes the story safer but subtler. Its path kept it out near the wide lanes of the inner solar system, flying a course that took it nearer to Venus in early November, and only much later approaching its most nearby moment for Earth, still almost twice our yardstick away in mid-December. That's why your social feed wasn't full of blazing streaks. The action was real, but it happened far out and mostly off stage from our line of sight. The calendar rhythm matters because it sets the tempo for everything else. A perihelion in late October meant the comet's brightest, gassiest phase overlapped with our worst viewing geometry. The weeks before and after became crucial. Before perihelion, we could watch the run-up as activity climbed. After, once it cleared the sun's glare and slipped back into our pre-dawn skies, imagers and big observatories could grab their data during the slow fade. This science plan then became a relay race. Mars missions and far-flung probes carry the baton through perihelion. Earth-based telescopes pick it up again in late November and December. Timing, distance, and geometry. Those three set the stage for how the story would be told. There's a deeper meaning tucked inside these numbers. A 1 1/3 yardstick perihelion hints at a visitor that is active but not extreme, a comet that wakes up decisively without tearing itself apart at a skim over the sun's surface. Distance shapes chemistry. Different ices switch on at different warmth levels, so a perihelion this far out favours certain gases and a particular rhythm of outbursts. It also shapes dust behaviour, the grain sizes that can lift off, the tails we see, and the way sunlight and the solar wind sculpt them into forms that change night by night. The date fixed the when, the distance fixed the how, and together they whispered clues about the what inside. And while the word perihelion sounds technical, the experience is simple to grasp. Imagine a snowball sealed in deep freeze for ages, then carried past a warm fireplace. At a cautious arm's length, the frost blooms and wisps of vapour lift away, bring it right up to the flames, and you risk a sudden, messy collapse. 3i Atlas chose the first version of that story. Warmth enough to sing, not enough to scream. The calendar gave us the day. The distance gave us the tune. We missed the live chorus from Earth, but our outpost heard it and took notes. By the time it arced past the sun and began to emerge from the glare, we knew what to expect. A traveller that had done its loudest whispering out of our view, now easing into the quieter half of its performance. The dates on the calendar, late October for the close pass, late November into December for our best follow-up, became markers for the chapters of its brief appearance. We measure that in days and months. The comet, on the other hand, measures it in sunlight, in heat absorbed and re-radiated, in the small bursts of gas that change its spin and sculpt its tail as it coasts back into the dark. That is the gift of the date and the distance. They turn a one-time cosmic encounter into a timeline we can plan for, a geometry we can use, and a story we can tell with clarity even as the visitor keeps moving on. First it was a whisper, then it was a shout. As 3I Atlas slipped toward the sun, its glow began to climb, slowly at first like dawn seeping through a window shade. Then, in the final approach to Perihelion, the trend bent upward more sharply. To the people watching the data come in, the light curve looked like a heartbeat, a steady rise, a quick surge, and a lingering echo. This wasn't just our eyes playing tricks. Something inside the comet woke up, and it woke up fast. Imagine a snowball that's been drifting in deep space for a very long time, coated in a sun-baked crust. For months, sunlight has been tapping on that crust, warming it a little more each day. Most of the time, the outer shell resists. It's dusty, compacted, a little bit like a layer of caramelized sugar on a creme brulee. Then a threshold is crossed. Hairline cracks appear. Pockets of buried ice meet warmth and vent like a tiny soda bottle opening under pressure. In a few hours, or even minutes, fresh gas punches through, carrying dust with it, and the comet's faint haze billows into something larger and brighter. That's the glow-up observers reported as 3I Atlas neared the sun. From Earth's surface, we missed the moment-by-moment details because the comet was too close to the sun in our sky. But instruments built to stare at the sun could afford to squint sideways. In those cameras, the comet's halo of gas, the coma, swelled and sharpened. Brightness is really just shorthand for cross-section. How much scattering stuff is in the way of the light. When dormant vents open, the comet suddenly has more stuff, more gas to push dust outward, more dust grains to reflect sunlight. Add to that the geometry bonus of forward scattering, dust throwing extra sunlight our way when the sun-comet observer angle gets just right, and you have the perfect recipe for a rapid rise. There are a few likely culprits behind a surge like this, and they may work together. One is fresh exposure. As 3I Atlas warmed, stress is built in its outer layers. Heat doesn't travel instantly through a body like this. It seeps. That slow seeping creates temperature differences that pry open seams. A small landslide or a flake of crust peeling off can uncover clean ice that hasn't seen starlight since another star was its sun. Clean ice turns into gas more readily than dusty sealed ice. Open a new patch, and you've opened a new nozzle. Another culprit is the kind of ice doing the venting. Not all ices wake up at the same distance. Water tends to dominate closer in, but more volatile ices, like carbon dioxide or carbon monoxide, can drive activity farther out, and then spike when the energy budget gets favourable. If 3I Atlas carries a richer than average mix of these eager ices, you'd expect its sunward side to kick hard as Perihelion approaches, blowing out gas that lifts a cloud of fine dust. Fine dust is a brightness cheat code. Tiny grains act like a million little mirrors, dramatically increasing the light we see. Spin matters too. Picture a garden sprinkler that starts to rotate faster as water pressure increases. Comets do something similar. Jets of gas act like thrusters, and as they fire, they can change the spin rate. A small change in the spin can re-aim vents, sweeping jets across fresh territory, or pointing them into space where their dust is better lit from our viewpoint. That means you can get a brightness jump even if the total gas output hasn't changed dramatically, because the same material is being presented to sunlight and to us in a more favourable way. There's also the subtle trick of phase angle, the way the sun illuminates the coma and tail from our perspective. When the comet is near the sun in the sky, the dust between us and the sun can glow more efficiently thanks to forward scattering. To a camera, that looks like an extra polish on the comet's halo, a soft but real enhancement laid over any physical increase in gas and dust. In plain language, the dust didn't just increase, it started shining in a geometry that favours us seeing it. Some watchers wondered if a small outburst or mini-fragmentation could be involved. That's not as dramatic as it sounds. Comets shed clumps. A weakly held slab can drift free, instantly increasing the available surface area and exposing more ice to sunlight. Even if the nucleus stays intact, a shower of fresh, fluffy dust can briefly pump the brightness before larger grains fall behind and the halo settles into a calmer look. The tail tells part of that story. Right after a surge, it can grow denser and more structured, with subtle kinks or fans that smooth out as the dust cloud expands and thins. How do we know we're not just chasing illusions from the glare of the sun? Because different instruments told a consistent tale. Photometry, the careful measuring of light, showed a climb that didn't match the slow, predictable brightening you'd plot for a quiet comet at this distance. Imaging showed the coma getting larger and the inner tail region changing texture. Timing matched the expected heat wave moving inward through the comet's surface. A delay between the first close pass to the sun's warmth and the strongest activity, like a frozen lake that doesn't crack the minute the air warms but waits until the deeper layers have caught up. All of this fits the personality we're beginning to assign to 3i Atlas: responsive, volatile, friendly, and capable of flipping from low to loud with only a small nudge. That personality matters because it becomes part of how we interpret everything else. A sudden glow-up tells us that the comet's outer layers are not a uniform, dead crust. They're patchy, strained, and primed to vent when given the slightest chance. It suggests veins of ice protected under dust, waiting for fractures to open. It argues for a mixture of gas types that doesn't match the average local comet perfectly, which is exactly what you'd hope to learn from an interstellar traveller. If you zoom out from the physics, there's an emotional beat here too. Think about how brief this window is. For years, decades, centuries, 3i Atlas was dim and silent. Then, in the span of a few orbits of our own planet, it came to life, shed a cloud, and painted a tail into sunlight we can measure and photograph. The spike in brightness isn't just a number on a chart. It's the moment the comet became legible to us, the moment its private chemistry translated into a public signal. And then, as quickly as it flared, the curve begins to relax. Gas pressure eases as the comet rounds the sun. The geometry shifts away from the angle that flatters dust the most. Jets sputter as the freshest vents frost over again. The glow doesn't vanish, it recedes. This is the signature of a natural traveller reacting to warmth, not a permanent change. The surge tells us what the comet can do when provoked. The fade tells us how it calms when the provocation passes. For storytellers and scientists alike, that sudden glow-up is a gift. It sets the rhythm for observations, hints at the ingredients in the mix, and reveals the fragile architecture of the surface without needing a close-up spacecraft flyby. It's the comet equivalent of hearing a voice crack with emotion. You learned something true in the spike that you might have missed in a monotone. With 3i Atlas, that truth is simple and thrilling. Give it a little heat, and it speaks up, loudly, briefly, clearly enough that even from the glare-soaked edges of the sun we could hear it. If you watched 3i Atlas around Perihelion and felt like the show was more haze than grit, you're not alone. Many comets announce themselves with thick, sunlit dust, clouds of tiny grains that act like a million mirrors. This visitor, by contrast, behaved like a gas fountain first and a dustmaker second. That difference matters, because it tells us what was waking up on the surface and what stayed stubbornly locked down. Start with a simple picture. Sunlight hits the comet. Buried ices warm up, gas escapes. Gas is the engine. Dust is the confetti. Whether we see a dust-led or a gas-led display depends on how easily that engine can grab the confetti and throw it into space. If the outer layers are loose, fluffy and full of small grains, the escaping gas drags a blizzard of dust with it, and the comet looks chalky and bright. If the outer layers are crusty, compacted, or made of grains that stick together too well, the gas can rush out through cracks without hauling much solid material. The result is a swollen, shimmering coma of gas with a relatively modest dust tail. The distance of the close pass helps set the stage. Water ice likes to take centre stage when a comet dives very close to the Sun, but farther out the first responders are the more eager ices, ones that turn to gas at gentler warmth. If 3I Atlas carries generous reserves of those early risers, you'd expect the gas engine to rev long before the surface is loosened enough to cough out lots of dust. That's exactly the recipe for a gas-led look. The coma inflates quickly, but the dust tail lags behind, thinner and more transparent than the dramatic fans we associate with some classic comets. Texture matters as much as temperature. Think of 3 kinds of surfaces: flour, sand, and baked crust. Blow across flour and you get a big dusty plume immediately. Blow across sand and you move grains, but you need a stronger push. Blow across a caramelized crust and almost nothing lifts. The air escapes through tiny gaps and doesn't carry much with it. Comet crust can evolve into that hardened state after many freeze-thaw cycles. It can also form as soft material near the surface sinters, grains welding lightly together over time in deep cold and radiation. If 3I Atlas arrived with a crust-like skin, then even a healthy blast of gas would slip out through fractures while most dust stayed put. Grain size tilts the balance too. Fine dust brightens a comet efficiently because small particles scatter sunlight in all directions. Coarser grains don't brighten the coma as much, and they're harder for gas to lift. If the outer layers of 3I Atlas are biased toward coarser, clumpier material, pebble dust instead of powder, then you get a dimmer, cleaner look. Lots of gas, modest dust, and a tail that seems shy compared with the swelling halo. Spin and vent placement can push this even further toward a gas-led behaviour. Jets behave like tiny thrusters. If the active vents aim into space rather than across the surface, they give gas a clear exit path without skimming along the ground to pry up grains. A slowly changing spin can also sweep jets over areas that have already been cleaned, so they find fewer loose particles to entrain. To our eyes, this looks like a steady or even surging gas coma, with only small, delicate dust streamers superimposed. The light itself gives away the mix. When a comet is dust-heavy, much of its brightness is neutral-looking sunlight bounced off solids. When gas is in charge, the inner coma shows telltale glows from specific molecules, fingerprints that show up when you split the light and look for narrow, bright features. You don't have to stare at a chart to understand the gist. Gas-led coma looks softer and more transparent, with edges that feel less sharply defined, because you're seeing light from excited gases laid over a relatively thin veil of dust, not a thick chalk cloud. Why might an interstellar traveller lean this way? One possibility is that 3I Atlas kept more of the eager ices that switch on earlier. Another is that its dust matured differently out between the stars. Cosmic rays and deep cold chemistry can change how grains stick together and how easily they break apart when heated. Imagine a pantry stocked with slightly different ingredients and a dough kneaded in a different kitchen. When it hits the oven of our sun, it rises in a way that isn't quite like our local recipes. There's also timing inside the comet. Heat doesn't zip straight to the interior, it creeps inward. Early in the approach, gas escaping through narrow paths might simply not have the muscle to lift much dust. Once enough cracks link up, or a small slump exposes fresh material, the dust response can catch up. That lag is a signature of a gas-led start. First the atmosphere around the nucleus swells, then slowly the tail fattens as more solids finally get dragged free. If you watched 3I Atlas over days rather than hours, you might have seen that patience rewarded, but the first impression stayed the same. The haze spoke louder than the grit. It's tempting to ask whether a quiet dust response means the nucleus is small or weak, but that's not the only reading. A reserved dust show can actually hint at strength, at least near the surface. A tougher shell resists erosion. Gas can find its way out of seams without sandblasting the entire face. That kind of restraint is interesting because it hints that the comet might preserve delicate layers just under the skin, keeping a record of its birth environment. For scientists, a gas-led perihelion is like being allowed to sniff a perfume without someone spilling the whole bottle. Gas leadership changes the look of the tail as well. When dust dominates, we notice the wide, curved stream of solids drifting along the comet's path. When gas is strong, we're more likely to notice the straighter, fainter features shaped by the solar wind. Ions being hustled directly away from the sun. To a casual observer, that can make the comet feel more ghostly, with fine structures that look like veils rather than a big chalk streak. It's still dramatic, just in a subtler, more delicate way. All of this feeds back into the story of where 3I Atlas came from. A gas-first outburst near a not-too-close perihelion points to an object that formed cold, stayed cold, and kept a healthy stash of the ices that wake up early. It suggests a surface that hasn't been pulverized by many hot passes around a star, because repeated cooking tends to fluff and loosen the outer layers. In other words, the gas-led show is consistent with a first-timer from another system. Plenty of fresh fuel, a skin that hasn't been overbaked, and a chemistry that leans toward the eager evaporators. And then there's the practical side. For observers planning their campaigns, gas leads, dust follows, sets priorities. You chase spectra early to catch the jets in full voice. You watch for subtle changes in spin that gas thrusts might drive. You prepare for the dust to make a quieter entrance, building slowly as the surface loosens and slumps. On the outbound leg, when sunlight wanes, you expect the reverse. Gas falls off quickly, dust lingers as a fading echo, and the whole apparition softens into the background. So if you felt the spectacle of 3I Atlas was more breath than powder, that was the physics talking. The engine roared, the confetti arrived fashionably late. In that gap between gas and dust, between haze and grit, lies a ton of information about crust, chemistry, venting, and the way an interstellar comet greets a new sun. It's a quieter kind of drama, but it's exactly the kind that lets us read the object's inner life without tearing it apart. At first glance, a comet's tail looks simple, a streak pointing away from the sun. Then you watch 3I Atlas night after night and realize the tail has a mind of its own, stretching, bending, splitting into layers, and sometimes doing the strangest trick of all, seeming to point toward the sun. That backward spike is called an anti-tail, and it isn't the comet breaking the rules of physics. It's geometry playing a clever illusion on our eyes. Think of the comet surrounded by different kinds of shed material. There's the fast, ghostly ion tail, gas that sunlight and the solar wind push straight outward, making a narrow, bluish spear that always points away from the sun. Then there's the dust tail, sunlit grains of rock and ice that move more slowly and curl along the comet's path, forming a soft fan that often bends. And finally there's the dust trail, a sheet of older, heavier particles that drift close to the comet's orbital path like breadcrumbs. Each of these responds to different forces and at different speeds. Put them together and you're watching a layered living sculpture. Why does any of it move at all? Sunlight has pressure, gentle but relentless. It pushes on tiny dust grains the way wind pushes a sail. The solar wind, charged particles flowing from the sun, sweeps up gas, shaping the ion tail like a windsock. Now add the comet's own motion around the sun, and suddenly the simple tail points away rule becomes a dance of curves and angles. Small grains behave like confetti caught in a gust. Larger grains are more like pebbles that barely budge. Gas reacts instantly. Dust lags. The result is a tail system that can change noticeably in hours and dramatically in days. So where does the anti-tail come from? Picture 3I Atlas leaving a thin, flat sheet of dust in the plane of its orbit, like flour sprinkled behind a moving hand. For most viewing angles, you see that flour as a broad, faint fan on the night side of the comet. But if Earth happens to cross that orbital plane, your line of sight skims along the dust sheet's edge. A wide pancake suddenly looks like a sharp line. From our perspective, that line can appear to stick forward, toward the Sun, even though each dust grain is still circling the Sun in the ordinary way. It's a projection effect, not the comet breaking rules, just the camera angle playing tricks. The timing of this matters. Anti-tails most often pop around the dates when our viewpoint lies close to the comet's orbital plane. Before, during, or after, the comet passes perihelion depending on the geometry. Observers of 3i Atlas described exactly this kind of flip. A subtle sunward spike, then a transition to the classic anti-solar tail, dominating the show again. In practical terms, the comet didn't flip its tail. We flipped our seat in the theatre, moving from a side view to an edge-on view of the same dust sheet. Grain size gives that sunward spike its staying power. The anti-tail is usually built from older, larger particles that left the nucleus days or weeks earlier. Because they're heavier, sunlight can't shove them around easily. They hang closer to the comet's path, forming a flat ribbon. When we look through that ribbon edge-on, the column of material is thickest, so it brightens and sharpens. As Earth keeps moving, the ribbon swings out of alignment, the spike fades, and the more familiar fan that points away from the Sun takes over visually. Meanwhile, the ion tail is doing its own quick change act. It's made of molecules that got stripped of electrons by sunlight and are now caught in the magnetic fields carried by the solar wind. That leash makes the ion tail thin, straight, and reactive. If the solar wind shifts or a gusty structure blows past, the ion tail can ripple, kink, or even disconnect for a short time before regrowing, like a streamer snapping in a squall. On a night when the dust tail looks steady, the ion tail can twitch. On a night when the dust tail is changing slowly, the ion tail can redraw itself in minutes. Rotation adds another layer. 3i Atlas isn't a smooth sphere with one hole. It's a lumpy body with vents. As it spins, those vents sweep across sunlight, turning on and off like sprinklers. Each jet throws out dust along a slightly different direction. Over hours, that can create overlapping feathers and fans that drift apart as the grains spread. If the rotation speed changes, because jets act like thrusters, the spray pattern changes too. That's why sometimes you notice subtle rays in the dust, as if the tail has ribs. You're seeing rotating sources painting the sky with repeating strokes. The phase angle, the Sun-Comet observer relationship, sweetens or flattens the entire view. When the angle lines up for forward scattering, dust grains become extra shiny. The inner coma glows, and faint structures leap out. Shift the angle, and the same structures look muted. This can amplify the anti-tail illusion. Catch the dust sheet edge-on at a high glare angle and it pops. Move a few days forward and it melts into the background, even though the dust didn't vanish. There's also a slow memory in the system. Dust you see tonight might have been released many days ago. The finest grains zip away fastest and mark the outer, curved parts of the tail. Medium grains fill the middle. The big grains cling to the orbital sheet and feed the anti-tail when geometry cooperates. If you could color code the dust by birthday, you'd see stripes. Yesterday's plume near the head. Last week's glow farther back. 2 weeks ago, lining the orbital plane. Without any color clues, your brain still picks up the pattern as textures. Soft halos near the head, delicate streamers along the edges, a hard sunward spike when the sheet turns edge on. Every now and then, a local event spices up the picture. A small surface collapse can dump a cloud of fresh dust. For a day or two, the tail fattens and the inner coma looks grainy. A change in jet direction can carve a fork or a fan, like a painter switching brushes. A gust in the solar wind can shear the ion tail and make it appear to detach, leaving a gap that fills back in later. None of these means the comet is in trouble. They're the ordinary weather of a small active world moving through a windy sunlit environment. For a storyteller, the anti-tail is gold because it looks so paradoxical. You can say, it pointed at the sun and people leaned forward. For a scientist, it's gold for a different reason. It encodes the dust's size and timing. The very fact that you saw a sunward spike suggests there's a strong sheet of large grains hugging the orbital plane. The length and sharpness hint at how fast those grains spread and how much the sun can push them. Track the spike over a few nights and you're tracking the invisible pancake, turning in space as both Earth and Comet move. 3i Atlas gave us a bit of everything: a responsive ion tail that traced the solar wind, a modest gas-led coma that grew and softened with heat, a dust fan that built structure as jets came and went, and a sunward spike when the orbital sheet lined up just right. It's tempting to call that chaos, but it's really choreography. Each piece follows a simple rule: gas rides the wind, small dust catches the light, big dust clings to the path, jets paint arcs, and our changing vantage point mixes those rules into a moving picture. If you want a simple mental model, use smoke for the ion tail, glitter for the fine dust, and sand for the big grains. Smoke blows straight away from the fan no matter how you turn it. Glitter swirls and seems extra bright when you face it into the light. Sand, once tossed, lands in a flat strip along the path you walked. Look along that strip and it becomes a sharp line pointing forward. Put those three in the sky at once and you have the restless layered tail of 3i Atlas. And there's a quiet joy in knowing that the weirdest looking moment, the anti-tail, actually reveals the comet's most patient story. Gas comes and goes in minutes to hours. Fine dust brightens and fades over days. But the big grain sheet, the one that makes the anti-tail possible, is a memory of activity from many days past. When you catch that sunward spike, you're seeing a time-stamped slice of the comet's recent life, stretched into a line by motion and made visible by the luck of perspective. For a brief window, the architecture of the comet's path turns toward us and says, "Here is the history, edge on, all at once." Then the angle slips, the spike softens, and the show returns to the familiar lesson. The tail points away, until geometry decides to surprise you again. Metals aren't supposed to fly. Not this far from the sun, not this early in the trip. Dust? Sure. Water vapour? Yes. Carbon-rich gases? Absolutely. But nickel, an honest-to-goodness metal, showing up in the glow around 3i Atlas well before a blistering close pass. That makes astronomers sit up. It hints that the comet isn't just shedding frosty breath. It's quietly sprinkling atoms forged in ancient starfires, releasing them into space like glitter in a beam of light. How do we even know it's there? By listening to the light. When observers split the comet's glow into its colours, certain razor-thin hues jump out, signatures that belong to specific atoms. Nickel has its own set of calling cards. When those appear in the spectrum, faint but undeniable, it means nickel is present in the gas around the nucleus, drifting in the coma rather than locked inside rock. That's the surprise. Nickel is normally tied up in tough heat-loving minerals. To see it in the wind, long before the sun's furnace is close, means something delicate is letting it go. There are a few ways that can happen, and the truth may be a blend. One path is sunlight breaking apart fragile carriers. Picture nickel not as a nugget, but as a hitchhiker bound into a flimsy molecule or perched on the surface of a tiny grain. Starlight can snap weak chemical bonds the way a sun-warmed sidewalk pops old gum loose. The freed atoms drift outward and, for a short while, become part of the gas halo. Another path is a kind of gentle sand blasting. The smallest dust grains have huge surface area compared to their mass. Even modest heating and light-driven effects can knock atoms off their skins, a process like whispering them into space rather than blasting them off with a blowtorch. Then there's the role of the comet's own breath. Earlier we saw that 3i Atlas is gas-forward. A lot of vapour, relatively restrained dust. That gas is a mover. It slips through cracks, leaks from vents, and flows across the surface. As it does, it can lift and waft ultrafine particles, specks so small they behave more like smoke than sand. On those specks, metals like nickel may sit in thin films or mixed into fragile coatings. Carried into the coma, tickled by sunlight, they release atoms into the gas phase. You don't need a roaring furnace for that. You need patience, sunlight, and time for the outermost layers to loosen. If that sounds subtle, that's because it is. This isn't a dramatic metal snowstorm, it's a soft exhale that instruments can notice only because the signal is clean and repeated, and that repeatability matters. A one-off spike could be a fluke, a crack opening over a metal-rich patch and then sealing again. But a steady presence of nickel lines across multiple nights tells a different story. The comet's outer skin may be laced with ways to free metals slowly, either through delicate chemistry inherited from its birth, or through the constant, quiet weathering of tiny grains under light and radiation. Why is this exciting? Because metals don't just tag along, they carry history. The ratio between nickel and iron, for example, is a clue to how dust formed and changed in the disk around the comet's original star. If 3i Atlas shows a balance that's unlike what we see in most local comets, it hints at a different kitchen, different temperatures, different mixing, different timelines. Even if the balance ends up looking familiar, that's a revelation too. It would say that the rules for building rocky bits, and for seasoning them with metals, are shared across star systems, not just a quirk of ours. This is where the comet's timing and geometry play in. Nickel was spotted before the sun got uncomfortably close, when the warmth is real, but not extreme. That sets some boundaries. It suggests we're not simply baking minerals until they give up atoms out of sheer heat. Instead, we're watching gentler pathways, sunlight loosening weak bonds, gas flow abrading surfaces, ultrafine dust acting as a shuttle for atoms that don't want to stay put. It also favours an idea that 3i Atlas arrived with a skin that hadn't been roasted by countless past flybys around a star. An overcooked surface tends to crumble into dust and dump solids fast. This one feels preserved, tough enough to resist dumping lots of grit, yet reactive enough to leak whispers of metal when nudged. Spin adds texture to the picture. As the comet turns, different vents take their turn in sunlight. A jet that plays across a patch rich in fine, metal-dusted grains could spike the nickel signal as it sweeps by, then ease as the jet rotates away. Over hours, that would look like breathing. Inhale, exhale, line brightens, line relaxes. Over days, as the thermal wave sinks a little deeper, new microcracks open and close, changing which patches contribute to the metallic whisper. That living, rotating pattern is exactly the kind of thing astronomers can track to link chemistry with surface geography. Meanwhile, the solar wind is sketching on the canvas. Ions, the charged wind-blown gases, form their own tails, while neutral atoms wander more freely until sunlight or collisions change them. If you imagine the coma as a tiny weather system, nickel atoms are like pollen drifting in the air, set loose near the source, spread by flows, sometimes ionized and swept, sometimes glowing briefly before fading into the mix. A shift in the solar wind can reshape their paths and tweak the lines we measure, which is why repeated observations are gold. The comet is telling a story, but the space weather writes in the margins. Of course, the immediate question many people ask is, does nickel mean the comet is breaking apart? Not necessarily. Metals in the gas don't require catastrophe. They can be the natural outcome of a surface that's being seasoned by light, puffed by gas, and gently eroded grain by grain. If anything, the calm gas-led profile of 3i Atlas argues for resilience, strong enough to avoid dramatic shedding, complex enough to release rare ingredients in small detectable amounts. There's a practical angle too. Nickel lines are relatively clean as tracers. If you can measure them alongside iron and a couple of common gases, you can watch how the mix changes from day to day and on the outbound leg. Does nickel fade faster than water vapour? Does it track with carbon-rich gases? Does it correlate with a particular jet direction? Those patterns become a map back to the surface, not a photograph, but a chemistry atlas that labels which regions are crusted, which are fragile, and which host the fine grains most eager to give up their metals. And because 3i Atlas is interstellar, every one of those patterns has extra weight. We're not just learning about a single, quirky object. We're taking a core sample from another solar system's building materials. If early, far-out nickel becomes a theme for interstellar comets, that suggests their birthplace environments tend to preserve delicate metal carriers, perhaps because the outer disks around their stars were rich in certain carbon or sulfur compounds, or because their dust grew in cooler, gentler conditions that favour fragile coatings. If instead 3i Atlas turns out to be an outlier, that's just as interesting. It means the galaxy's recipe book is broader than we thought. In the end, nickel in the wind is exactly the kind of quiet clue that makes this visitor irresistible. No fireworks, no dramatic breakups, just a thin, persistent signal threaded through the light, telling us that even in a soft gas-forward display, the comet is sharing the deepest parts of its story. It carries rocks, and those rocks carry metals, and those metals can be coaxed into the air by nothing more than sunshine and the comet's own breath. That's a poetic image, yes, but it's also a practical one. It means we can read the comet's past with instruments we already have, from distances that keep us safe at times when the geometry finally returns in our favour. As 3i Atlas slides away from the sun and the loudest gases quiet down, the nickel lines may change, soften, shift, or even linger if fine grains keep whispering atoms into space. Watching that fade isn't just a wrap-up, it's the second half of the test. If the early nickel came from fragile carriers near the surface, the signal should fall off as those layers are spent. If it came from ultra-fine dust lofted into the coma, the signal may outlast the gas, glowing faintly as the dust drifts and thins. Either way, the ending will rhyme with the beginning, and in that rhyme we'll hear what kind of skin this interstellar traveller wore when it first felt our sun. So yes, metals aren't supposed to fly. And yet around 3i Atlas they did, calmly and clearly enough for us to notice. A metal's whisper, caught in a beam of light, turns out to be one of the truest things this comet can say about where it came from and how it's built. You don't need a furnace to hear it. You just need patience, a spectrograph, and a visitor willing to talk. When Earth had to look away because the sun's glare swallowed the view, the robots kept watching. Coronagraphs, those clever cameras that block the sun with an artificial eclipse, caught 3i Atlas slipping past the solar limb and turning up the volume. On Soho's long-running LASCO imager and NASA's new GOES 19 coronagraph, the faint puff around the nucleus swelled into a clearly extended glow, not a pinprick, and the brightness climbed faster than a typical local comet at a similar distance. Stereo A, cruising well away from Earth, filled the gap too. Its heliospheric images saw the same upswing, letting astronomers trace the rise even while ground telescopes were blind. Together those platforms stitched a continuous light curve through the very hours we would have missed, proving that the flare-up was real, not a trick of geometry. The colour was a clue all by itself. In Soho's filters the comet looked unusually blue. Astronomers speak for light dominated by glowing gas rather than sunlight bouncing off dust. That fits the personality we've been seeing all along. Gas leading the show, dust arriving later. It also matches the way the coma sharpened in the coronagraphs. A more transparent, vapour-rich halo with fine structure close to the head, rather than a thick, chalky fan. If you imagine a hiss of vapour outrunning a sprinkle of grit, you've got the picture those spacecraft sent home. Meanwhile, Mars had the good seats. In early October, as 3i Atlas slid by the red planet's neighbourhood, ESA's ExoMars trace gas orbiter turned and snapped it. Just a fuzzy bead against star streaks, but the closest space-based view to that point, and proof that planetary missions could join the chase. Mars Express pitched in as well. From there, the comet was far enough from the sun's glare to pick out, even as Earth's telescopes were forced to stand down. It felt like a relay. Mars handed the baton to the solar sentinels just as the sun swallowed our line of sight. Back near the Sun, GOES 19's Coronagraph added a fresh perspective from geostationary orbit. Designed to watch space weather, it started recording the comet nights before Perihelion, and, at the height of the glare, resolved the head as a little puffball rather than a star-like point, evidence that the gas halo had ballooned. Amateur analysts even teased out brightness estimates frame by frame, confirming the rapid surge while everyone on the ground was effectively looking into daylight. Stereo A's Core 2 and High 1 cameras and Soho's Lasco C3 all told the same story. A steady climb that bent upward into a quick ramp right around the solar swing-by. There were hints in the texture too. In the coronagraph fields, the tail nearest the sun's edge looks delicate, more like a veil than a thick brushstroke, while farther out, thin streamers came and went as the solar wind shifted. That's the ion component responding to changing space weather. A gusty patch can kink the tail or briefly thin it, then the flow smooths and the line regrows. Watching those ripples lets scientists sample the solar wind in real time with the comet as a windsock, something ground observers can rarely do so close to the sun. The most striking part was simply that we didn't lose the thread. Normally, a comet slipping into conjunction is like a stage actor exiting behind the curtain. You guess what happens offstage and wait for the re-entrance. This time, the offstage microphones were hot. Soho, Stereo A and GOES 19 kept the signal coming. Punch added heliospheric context. By the time 3i Atlas emerged into dawn skies again, we already knew it had spoken loudly in gas. That continuity turns guesses into measurements. It tells us the spike wasn't a one-frame flare, but a sustained response to heat. Cracks opened, vents woke, vapour surged, dust followed more softly. Even before the solar swing, other spacecraft had been quietly laying groundwork. From Earth orbit, Hubble had taken an early look months before Perihelion, nailing the interstellar nature and giving teams a baseline image of the coma's shape and the nucleus's shrouded brightness. Then, just as the sun began to dominate the geometry, NASA's Swift Observatory sniffed for water's fingerprint and found the telltale hydroxyl glow. Another piece of the chemistry puzzle that explains why the coronagraph colours looked gas-heavy near the sun. These advanced snapshots meant the Perihelion surge didn't arrive in a vacuum. It arrived with context. If you step back and watch the choreography, it's elegant. Mars picks up the comet early, confirming it's active and on schedule. Solar images catch the handoff, tracking a growing blue-leaning coma as the comet slips behind the sun from Earth. As soon as elongation widens again in November, the ground will take over, but with a script in hand. Here's how fast the light rose, here's how large the inner coma looked in the coronagraphs, here's how twitchy the ion tail was under changing solar wind. That script tells observers what to look for on the outbound leg, whether the gas fades quickly, whether dust lingers as a ghost trail, whether jets keep nudging the spin. There's a deeper payoff to this eyes everywhere approach. Interstellar visitors don't loop back for encores. We have to get their whole arc in one pass. Spacecraft made that possible. No gap at the key moment, no guessing about what the sunside performance looked like. We learned that 3i Atlas gets bluer and brighter under heat, that its halo can be resolved as a true cloud even in the harshest glare, and that its tail reacts like a sensitive windsock. All of that feeds the bigger questions: what it's made of, how its crust behaves, how an ice-rich body shaped around another star responds to our sun's light. And because the cameras never blinked, we can tie each answer to an exact place on the timeline, not just a hunch. In the end, what the spacecraft saw was simple and beautiful. A quiet traveller from somewhere else, roused by warmth, hissing to life and painting a fine, gas-rich veil into sunlight, caught in the act by a ring of distant, patient eyes just when our own had to squint. The result is a clean record of the moment that matters most, a bridge across the glare, and a lesson for the next time an object from another star cuts through our sky. Perihelion is the moment when a comet's secrets stop whispering and start speaking plainly. Heat is the translator. As 3I Atlas swung through that closest approach, the sun did what no telescope can do from a distance. It pressed on the surface, stressed the crust, and forced the interior to answer. What came back was a clear message. This traveller is layered, lively, and volatile-friendly, awake enough to surge, strong enough not to fall apart, and different enough from our local comets to prove it was made in another kitchen. The first thing we learned is about the skin it wears. For weeks the activity had been cautious, as if a firm shell were rationing what could escape. Near Perihelion, that changed. The heat wave finally penetrated shallow depths, and hairline fractures turned into pathways. Gas didn't ooze, it hissed. But even then, the surface didn't crumble into a blizzard of grains. Instead, much of the energy escaped through vents, localized jets that inflated the coma while leaving the overall dust output comparatively restrained. That balance tells us the outer layers aren't loose talc. They're a crust that can withstand a hard push, yet still open seams when the sun insists. In comet language, that's young behaviour, not baked and pulverised by many close solar flybys, but also not a fragile snowball ready to explode. The chemistry of the surge sharpened the picture. A gas-led brightening right at perihelion points to eager ices driving the show, species that wake at gentler warmth than water, and then supercharge activity when the energy budget peaks. It's the difference between a kettle that suddenly screams and a pot that only begins to simmer. In practice, that means 3I Atlas likely carries a generous stash of early riser volatiles near the surface, with water taking a stronger role only when cracks connect deeper pockets. That hierarchy is a fingerprint of birthplace, a cold nursery far from its original star's furnace, where fragile ices could condense and survive. The tale confirmed the story while adding its own chapter. Right around perihelion the scene looked layered rather than loud, a delicate straight ion streamer reacting to the solar wind like a windsock, a softer dust fan sketching the comet's motion, and, when geometry lined up, a sunward spike carved out of the flat sheet of older, heavier grains along the orbital plane. The way these elements traded prominence told us about grain sizes and release times. Fine dust lit the inner halo for only a short window. Large grains lingered as a rigid sheet and produced that anti-tail illusion when we looked edge-on. The ion tail twitched in step with gusts in space weather. None of that requires fireworks. It requires a nucleus that vents cleanly and a vantage point that changes quickly, both of which Perihelion delivered. Timing mattered just as much as ingredients. The light rise didn't follow a lazy curve. It bent upward, peaked, and then began to relax. That shape encodes a simple thermal truth. Heat doesn't leap, it creeps. The outer millimeters respond first. Deeper pockets take hours to catch up. Once the comet passes the point of maximum sunlight, the pressure eases but doesn't collapse immediately. That lag, heat sinking, gas surging, then fading, became our ruler for the shallow subsurface, a way to estimate how quickly the skin breathes and how easily it trades trapped frost for escaping vapour. Perihelion, in that sense, worked like a non-contact biopsy. Spin left fingerprints too, jets are tiny thrusters. As they fired hardest near perihelion, they nudged the comet's rotation, just a little, but enough to re-aim vents and sweep the spray pattern across fresh terrain. To the eye, that looked like subtle ribs and fans near the head that shifted over hours, a living spray paint effect. To the mind, it meant we could tie chemistry to geography. When a certain jet lit up, a certain mix strengthened. When the jet rotated away, the mix softened. That's the beginnings of a crude map. No pictures of the nucleus required, only a moving pattern translated into places on a spinning, lumpy world. Strength versus fragility is always the big question at the sunside turn. Did it shed chunks? Did it split? Did brightness spikes come from collapses or from vents waking up? The perihelion record argues for resilience. We saw a surge consistent with opening pathways and a modest dust response more in line with surface peeling than wholesale sloughing. If a dramatic breakup had occurred, the tail and coma would have worn it loudly. Thick, gritty structure blooming and then decaying chaotically. Instead, we saw a traveller that could take the heat, flex and keep going. That alone is valuable. It means 3-Eye Atlas can carry its layered story out of Perihelion intact, giving us an outbound leg to test what we think we learned on the inbound. The most elegant confirmations were the quiet ones. Earlier hints of trace metals in the gas, Nichols' whisper, make more sense in a perihelion context where fine grains are lofted, sunlight is fierce, and fragile surface coatings can release atoms without brute heat. The gas-led coma near maximum sunlight agrees with that. More vapour to carry ultrafine particles, more opportunity for light to tease atoms free, still no need for catastrophic melting of rock. Put together, that says the surface is chemically rich in delicate ways and mechanically strong in structural ones, a rare but telling combination. Perihelion also helps separate hype from physics. When interstellar visitors act oddly, it's tempting to reach for exotic explanations. What the Sunside data showed is that 3-Eye Atlas doesn't need any. A CO2 and CO friendly mix waking early, vents opening under stress, jets altering spin a touch, dust responding by size and age, geometry making illusions. It's all cometry, just tuned by a different recipe of ices and a crust with more backbone than fluff. That's the good kind of weird. Different enough to teach, natural enough to trust. What then do we carry forward? First, a permeability map in words. The crust is sealed in most places, fissured in enough places to vent strongly, and sturdy enough to resist becoming powder under stress. Second, a chemistry sketch. Early rise of volatiles close to the surface, water joining in through connected cracks, trace metals available through fragile carriers on ultrafine dust. Third, a dynamics note. Jets can torque the spin and re-aim activity on hour-to-day timescales, which means brightness is as much choreography as it is fuel gauge. Finally, a tail ledger. The ion streamer is the sensitive windsock, the fine dust fan is the quick fade chorus, and the big grain sheet is the patient historian that occasionally turns edge on and pretends to point at the sun. All of that spills into testable predictions for the outbound leg. Gas should fall faster than dust as sunlight wanes. Colours should drift from gas-dominated to dust-tilted. The inner coma should shrink and soften. Large grains should keep sketching the orbital sheet and may stage a second anti-tail cameo as geometry changes. If jets keep chattering, small nightly changes in the tail's inner texture will continue. If the surface settles, the look should stabilise and the light curve should smooth. Either way, watching the fade will be as important as watching the flare. The echo after Perihelion often tells you as much about structure as the shout at Perihelion. There's a bigger, quieter lesson humming underneath. Perihelion gave us a controlled experiment. We couldn't choose the lab or set the thermostat, but the sun did it for us, turning the dial up and then down while a ring of eyes recorded the response. From that we learned that 3-Eye Atlas behaves like a preserved first-timer from a different star. A tough skin over lively ices, efficient vents, and a dust system more architectural than explosive. That's not just a description, it's a bridge. It links this object to the infant disk it came from, to the temperature lines in that disk where different ices freeze, to the way dust grains grew and stuck together before any planet existed to claim them. So when we say, here's what Perihelion taught us, we're really saying, here's what the sun coaxed this traveller into revealing. It told us it was built cold. It told us it was capped but not caged. It told us it would rather breathe than crumble. And it told us, in the language of tales and timing, that the same simple forces shaping our comets, sunlight, wind, spin, geometry, can sculpt an interstellar visitor into familiar forms while leaving its accent intact. That's the gift of Perihelion. Not a single dramatic scene, but a full, revealing conversation one that continues as 3i Atlas glides back into darkness, and we listen carefully to how the echo fades. When a rare visitor like 3i Atlas swings through the headlines, the internet starts to fizz. One clip claims it made a physics-defying turn, another insists the tail vanished, so it must be a craft. A third swears the brightening curve is impossible for a natural object. It's easy to get swept along. Strangeness is half the fun. But if you hold the camera steady and look at what the instruments actually recorded, the picture gets simpler, sharper, and, honestly, more interesting. First, the "it changed direction" claims. A comet's path against the stars is a projection. You're watching a three-dimensional arc painted onto the inside of the sky. As Earth rotates and orbits, the viewing angle shifts hour by hour. Stack that with the comet's own fast motion, and you'll see apparent bends, stalls, even wiggles if the timestamps are uneven or the video is stabilised on the wrong reference. None of that means the object is steering. Gravity is doing exactly what it always does. We're the ones moving our seat in the theatre. Second, the no tail equals engine shut-off posts. Tails are not one thing. Gas tails can be thin and straight, responding to the solar wind. Dust tails can be wide and faint, responding to sunlight pressure. And the dust trail, a sheet of older, bigger grains, can masquerade as a sunward spike when we view it edge-on, creating the anti-tail illusion. Exposure, processing, and geometry decide which piece you notice on a given night. A short exposure might catch only the bright inner coma and make the tail look gone. A long one can bring out gauzy streamers you didn't know were there. Switching filters can make a gas-rich halo pop blue-green one night and look neutral the next. It's optics and physics, not a throttle. Third, the impossible brightening meme. Comets don't brighten smoothly because their surfaces aren't smooth. As 3i Atlas warmed, cracks opened, fresh ice met sunlight, and jets switched on like sprinklers sweeping across a yard. That makes the light curve bend upward and then relax. Exactly what you expect when a crust yields in patches instead of melting all at once. Throw in a favourable observing angle, dust grains throwing extra light toward us when the sun, comet and observer line up, and a surge can look dramatic without the object doing anything supernatural. Fourth, the over-processed wonders. Contrast stretching can carve dark wings around a bright core and make a perfectly ordinary coma look like it has rigid panels. Denoising can invent feathers and spokes. Hot pixels and cosmic ray hits can masquerade as escorting lights. None of that invalidates amateur work. Some of the sharpest early clues come from backyard telescopes. But it does mean we put the pretties next to the calibrated measurements before we draw conclusions. A good rule of thumb: when a claim goes viral, ask 5 simple questions. What were the camera settings and filter? Is there an independent image from a different site the same night? Does the motion match star charts once you correct for Earth's rotation? Could the viewing angle explain the effect? Anti-tail, forward scattering, or a solar wind kink? And finally, does the measurement include comparison stars? That is, were we measuring the comet's brightness against nearby stars taken in the same conditions? If those answers are vague, the take should be cautious. None of this drains the magic, it focuses it. The evidence says 3i Atlas is a natural comet with an interstellar accent, gas forward near Perihelion, with vents that can wake suddenly. A tail system that looks restless because gas, fine dust and big grains obey different rules, and a surface strong enough to breathe without falling to pieces. The oddities are the kind we can test. Chemistry in the light, changes tied to rotation, tail structure mapped to grain size. That's the good story. Not it must be artificial, but look how much nature can do with light, ice, dust, and wind when you see it from the right angle. What matters next is how we listen on the way out. The outbound leg is where a lot of hunches get proved or pruned. As the elongation from the sun grows and the comet slides back into dark pre-dawn skies, The baton passes from solar sentinels to ground-based telescopes and long-exposure imagers. Expect the voice to change. Gas sings loudest near peak sunlight. As the heat fades, the gas lines soften first. Dust keeps humming a little longer. If the past is any guide, 3i Atlas will look cleaner and more delicate week by week. A shrinking inner coma, a dust fan with lower surface brightness, and a straight fainter ion streamer that comes and goes with the solar wind. Colour will drift too. Early on, the halo looked bluer in some instruments, a sign of glowing gas layered over a modest dust veil. Outbound, the balance should tilt toward neutral as dust takes over the light budget. Polarimetry, measuring the preferred orientation of scattered light, can help here, because it's especially sensitive to grain size. Higher polarization signals tend to whisper smaller, fluffier grains. Lower ones often mean bigger, glassier particles. If observers can keep a weekly cadence, we'll watch the grain mix evolve instead of guessing it from a single night. Spin state is another thread to pull. Jets act like thrusters. When they're strongest, they can speed up or slow down the rotation by tiny amounts. The coma hides the nucleus, but its inner texture often carries the rhythm of the spin. Repeating fans and ribs that drift around the head over hours can give a rotation period and show whether that period is changing. A subtle lengthening on the outbound side would say the jets eased off in a way that reduced their torque. A steady period would argue for balanced, persistent vents. Either result tells us about the shape and stiffness of the crust. There's also the delayed reaction game to watch for. Some ices can rearrange their structure as they warm, releasing trapped gases later than you'd expect, like a frozen sponge that wrings itself out after you've already moved away from the heat. That can trigger small, late outbursts on the outbound path. If we see brief brightenings that fade over a day or two, with a puffier inner coma but no dramatic breakup, that's a strong hint that deeper layers are still catching up to the sun they just left behind. Geometry will keep throwing us treats. If Earth crosses the comet's orbital plane again in the months after perihelion, the dust sheet could turn the edge on a second time. That's when a lean, sunward spike can reappear, the anti-tail trick returning for an encore. It won't mean the comet flipped its physics, it'll mean our sightline threaded the same flat ribbon of big, slow grains. Catching that alignment on both the inbound and outbound legs is gold, because it lets modelers timestamp the dust by age and speed, then back out how strongly sunlight pushed different grain sizes. Don't be surprised if you hear less about water and more about the early riser gases as the glow fades. Water usually dominates very close to the sun. Farther out, carbon-bearing ices can shoulder more of the load. On the outbound side, those species can linger in the spectra, even as the total brightness drops. Pair that with any lingering hints of trace metals, from ultrafine, sunlight-tickled dust, and we'll have a chemistry arc that runs from first whisper to last echo. If the nickel whisper fades quickly, it suggests fragile surface coatings were spent near perihelion. If it lingers, it points to a slow leak from fine grains hanging in the coma. Practical reality check. This is likely a telescopic show, not a naked eye beacon. For imagers, short focal lengths and wide fields early on help catch the full sweep of the dust fan. Later, deeper stacks at longer focal lengths can tease out structure near the head. Narrowband filters that target specific comet gases earn their keep in the first weeks after perihelion. Broadband imaging takes over as dust dominates. Amateurs with steady skies can contribute real science by repeating the same framing and exposure night after night. Professionals will fold those light curves into the bigger picture with spectra and polarimetry from large telescopes. Some dreams will surface. Could radar ping it? Could a space telescope swing to it? Could a fast flyby mission chase it down? Radar is almost certainly off the table at this distance and size. The coma outshines the core and the range is brutal. Space telescopes may grab targeted snapshots if schedules and brightness cooperate, but the real backbone will be a global ground campaign. And a flyby. Not this time. The lesson of 3i Atlas isn't that we missed our chance, it's that we're finally rehearsing well. Each interstellar visitor sharpens the playbook for the next. Faster observations, smarter coordination, and instruments aimed where they matter when the sun takes centre stage. Beyond the images and charts, the outbound leg is where the narrative lands. If gas fades faster than dust, that confirms the gas-first personality we saw near the sun. If the inner coma stays tight and transparent rather than chalky and turbulent, the strong crust with tidy vents picture holds up. If small, late outbursts dot the light curve, the comet will have told us it keeps secrets in layers that only give way after the heat is past. And if the anti-tail shows up for a final bow, the dust sheet model gets a beautiful public proof. Then comes the quiet ending. The tail thins to a whisper. The halo shrinks until it's a soft star in long exposures. The visitor slides outward, past the reach of small telescopes, beyond the deep cameras, back toward the big cold between the stars. We won't see it again, but we won't need to. We'll have the timeline from first detection to last frame, the chemistry from gas loud to dust dim, the spin hints, the tail choreography, the geometry tricks, the way our instruments heard an interstellar accent in the voice of a very natural comet. The hype will have come and gone. The evidence will remain, written in light, and that, in the end, is the best kind of ending. 3i Atlas leaves us not with a conspiracy to chase, but with a playbook to keep. How to separate spectacle from signal, how to listen when the sun asks the questions, and how to read the soft, fading notes of a traveller that will never circle back. The next time a stranger drops in from another star, we'll be ready. Not to shout, "Mystery solved," but to do what we did here. Follow the trail of measurements, let the physics do the talking, and tell the story cleanly as the visitor heads for the dark.